welcome Fred Hebert.
Thank you. So I'm talking about how to keep a system running forever. In truth is that I don't keep systems running entirely. Most of them, they're partially running. There's always a part failing somewhere in some extent. I'm working with Heroku. We're writing the routing system in HTTP and stuff like that in Erlang. And there's always something that goes wrong sooner or later. And we're also not really keeping them alive forever. That remains to be proven. At some point, AWS entirely went down, and so we went down with it. So this talk is probably better titled How We Keep System Partially Running for a Prolonged Period of Time. The basic lesson to have in there is that everything is terrible. The network is terrible. The network is always going to be full of pain. If you trust a network to be good, you're going to have the worst time in the world. Everything can fail. Connections get to be open only in one way. Stuff fails, stuff times out. They can come back up in all kinds of scenarios you hadn't seen coming. It's just a terrible, terrible thing. The libraries are buggy. Even the ones without bugs are buggy. The thing is that a system is easy to reason about as long as the load is low on it. And as the load gets higher and higher and higher, a library that doesn't have a pure code error might start behaving a bit funny with all the different scheduling options, or maybe just under load, and then it starts timing out in funny ways. And you figure out that the design of the library, although the behavior is completely fine, doesn't scale up always the same. And that will happen with most libraries that you will write yourself, and with many libraries that you just download from online. There's nothing to protect you from that. Communications between humans is hard. Garrett touched that this morning. Everything we do is impacted by that. You have super fun concepts like Conway's Law that tells you that the code that you have will take the shape of the team that programmed it. If you have 3 people in the team, your system will be divided in 3 major components and stuff like that. That's how you get God objects in OOP. There's one guy or one person that knows a lot of the system, just does a lot of work, and that object grows until only one person can touch it. Microsoft has done super interesting research that tells you that it's easier to predict how many bugs there will be in the system if you look at the team structure and code ownership than if you look at code metrics like cyclic dependencies or code churn and stuff like that. So how you communicate and think or talk with people is very, very important, nearly as much as everything else in there. The specifications will be wrong. You've got three types of programs out there. You've got a program with a static specification that never changes. You could see that as a Sudoku solver. You just put it in there, it gives you the answer, it's good or bad, and that's it. Then you have a second type, which is a specification that is static, but you have a quality assessment to do about it. So in that case, it could be a Sudoku grid generator where you want to have a given difficulty that goes in it, or a chess game player where the rules are set in stone, but there's a different quality of the competition you will get from that thing. And then you get the rest of the programs where the specification is more or less right for a short period of time. And as people use the system and get used to it and try to have fun with it, they become dissatisfied with it and ask for improvements. And as you go, the mere existence of your system makes the specification become wrong. So whatever you do with a specification is sooner or later going to be wrong. And then I make mistakes all the time. I crash systems, I release bad code. Other people on the team do it also. So everything is terrible. System in general might look a bit like that. So we get the gist of it. There are dinosaurs, they're rushing through, they're terrorizing people. Sure, the wall is kind of broken, and then the Triceratops just goes through right there, and the Tyrannosaurus says he's eating salads. But generally, the point is done, and the kids are happy. Dinosaurs are scaring people and eating the food. Most of the systems we put in production are like that. The bugs remain in there for a very long period of time. And what we get is the law of diminishing returns. Everybody knows that the longer you chase a bug, the more expensive it becomes. And at some point, you just decide, yeah, the bug's going to stay there and it's just going to pay the fee on that. And that's how it remains. And so we have to plan systems for that. So you have to prepare for the worst case. I'm selfish, impatient, a little insecure, and make mistakes. I'm out of control, and at times hard to handle. But if you can't handle me at my worst, then you sure as hell don't deserve me at my best. That's a quote that's usually attributed to Marilyn Monroe. It's kind of crappy with people, but it's really, really good with my software. So how do you deal with software in this worst case? You want to be able to kill it, start, and get back up like nothing happened. The worst case that you have The worst case that you have is that everything crashes and shuts down. And what do? You want to come back up really, really quickly. And once you have that basic case handled of something very difficult, everything else, in the worst case, is that. And in Erlang, we have the very, very fast shutdown. We don't always have the very, very fast come back up. So sometimes if you do it in Erlang, a guy just stays on the ground for like 5 minutes and then comes back up. So the ground rules are, state is terrible. State is the most important thing in your application. You put it in a database and you expect the database to live longer than all of your code. State is also where the pain lives. That means that the most important thing is that the programmer suffers. You want to get rid of all the bad state you might have. You want to keep only the good state. If the state starts to be bad, you're going to have a very, very hard time. And you want to drop all the bad state as soon as possible. It's a bit like, I guess, eating cereals. And if you find out that the milk is spoiled, you don't just keep eating it and say, well, I'm guessing I'm going to fix that tomorrow. You just stop it right there. It's terrible state. You throw it away and you start fresh. Don't know why we want to keep all the buggy data in the system in the pipeline. So we need to know what kind of state we can go back to. Something stable, something predictable, something we can reason about. Fortunately, we have all the mechanics for shutting down and coming back up ready. The problem is that as we're people and imperfect, we just mess it up all the time. Who here has code that looks like that? Just raise your hand. Yeah, there's a few of you. I know there are more than that. Because if you've ever complained about the supervisor should have a cooldown period to retry stuff, you're probably doing it wrong like that. This is usually wrong. And the problem about that one is that starting a process is a synchronous operation. And if I look at it, I'm going to see something like, yes, I get a new state is connected, therefore I should be able to assume that I'm going to get a connected process every time. And the fact that I have that connect right here tells me that you're a big liar if you put this stuff on top. Because what you're telling me is you're going to get a connected process, you didn't tell me that it could be disconnected, which is false. So what you want to do is something a bit more like that. And this is a tiny difference. What you're doing is instead of guaranteeing a connected client, you start guaranteeing a client that might or might not be connected. And this is a tiny, tiny change in your code. It's a huge change in the applications you have. So the main difference you have in that one is that if the client gets disconnected, it's no longer the client itself in that code right here that makes an assertion that your entire system should go down. If I'm connecting to your main database where all the data lives, of course you can't boot without it. If I'm connecting instead to a metric system that's entirely optional or to report to people, then it's entirely optional. And if I shut down the system on that, then the client library just decided to steal the entire control of the application and say, you know what, I really like what I do as a living, and if you don't have me, you should not be running. It's kind of being a jerk move in there. So you want to be able to go into all your supervision trees and all your init functions and figure out what it is that you guarantee, what is absolutely essential for your application to be up, and what is actually optional and how you deal with it when it's not there. And we have all these tools, and you should be able to look at your supervision tree and everything and be able to figure out, yes, this is crucial data, this is actually optional, this is crucial, this is not, and whatnot. If you don't take these steps, then you're losing the guarantee that the guy can come up. He might just come up with a broken arm or something, and if it's a broken leg, it doesn't come up at all. Right. So then we have to plan for overload. This is the next main reason for crashes. Irina treated about this a little bit. I just like the animation. I got to let go a few times, even if I'm tight in there. All right. So your system is a bathroom sink. You have the edge of the system where all the output goes, and you have deep in the system where the data gets outside of it. So it can be a database, it can be a log file, it can be an API to an external application. Data comes in, data comes out. Under regular operation, everything is fine. You put the data, you just look at the kitchen, at the bathroom sink, everything goes down and down and down, and then you're done. Yeah, everybody's happy with the system. From time to time, there's a bit more overload. And what might happen is that, yeah, water is coming up, eventually it subsides, and you go back to normal operation, everybody's happy. Now the problem is that maybe you're getting more popular, or maybe someone has seen you on Reddit, or maybe it's been on Slashdot, and bam, you've got a crash dump. And then you look at the crash dump and you say, or you go on the mailing list and ask people like, why isn't there something that just randomly kills processes in the Erlang VM? There's one of them maybe every month, and yeah, prolonged overload. So you look at it and say, yeah, well, I'm just going to make the system able to handle more memory. That's how you're going to fix it. If we make it bigger, it's going to handle more flow. That's science. So you got the proof. You look at the crash dump, and you saw that the sync process right there was obviously having 1 billion messages, and that was not enough space. So what we do, we let the process handle more stuff. So we just bulk up the system after a few weeks of refactoring. We look at it, and then it crashes again. So you look at the crash dump, and then you see, oh yeah, that part down there, the drain, that's where it's not actually able to get data fast enough. So you just spend a few more weeks refactoring, and then you get bigger drains. Then you have that super system that's able to go fast and fast and fast. And you figure out that if you crashed after 1 or 2 days of activities before, now it takes an entire week, but you still crash. So you look at it and you go, oh yeah, it looks like the pipes are not able to absorb enough data. Of course, what do? Well, you're a good software engineer, and you go there and you measured everything, and you know the pipes are too small, so you optimize it. Now you have the bigger pipes, and you have that Hulk of a system that's super, super strong. It's able to handle everything. It's terrible to maintain because it has all these hacks to make sure everything is the fastest. Then you run it for a while, and it takes like a month, and after a month it's still running, and you're like, yeah, this is great. You just turn off the pager, and then boom, it explodes during the night, and then the day after you lose your job. So what happened is that you spent like 6 months optimizing everything, and the actual true bottleneck was that bit right there that you don't control. You don't necessarily control the disk speed, you don't necessarily control the APIs you talk to, but they still impact the speed at which your system can go. And what we just figured out is that all that stuff that we thought was not premature optimization because we measured it was actually artificial optimization because that was a true bottleneck, and it's worth nothing going faster than this one, even with everything. So we got paid to solve the wrong problem, which we're great at. So we have to pick what has to give, and Irina touched on that topic earlier today. You've got the option to block an input, which is back pressure, and it's the equivalent of having a bouncer in front of a club or a bar or any other shady establishment, just looking at how many people are in there and keeping people out. You can only get in once other people go out, or if you're judged attractive enough to disregard the rules. To drop data on the floor, you have the option of looking at it like a dam, a hydroelectric dam. If you've ever seen a picture of it, or if you had the luck to see a real one, it's like a picture but bigger. You'll see that they have usually a spillway. So you have that dam with the huge reservoir where water just accumulates all the time, and there's a limited capacity of what can go through the turbines at any time. So when the water gets too large, there's like a spillway on the side where water just goes there, it doesn't ever touch the system, and you keep having something useful. So Irina called it dropping data on the floor. That's exactly the term I'm using here. You just don't handle the requests, you throw them on the floor. Ultimately, what you do there is entirely a business decision. So you can flex the engineering muscle, but unless the customers or just the people who run the business agree with it, it's a terrible decision. So for back pressure, the default option we usually have, and this is something that a lot of Erlang programmers don't get at first, the first option is to make everything synchronous. And we don't get it because it's usually implicit. If you're programming in Ruby, in Python, even in C and whatnot, a function call returns when it returns. And that means that the back pressure is implicit to your system. When it can't go faster, the entire system just slows down, and you see, well, the system is slow. What could go wrong? And that's a problem in there, is that the back pressure is implicit. In Erlang, we tend to lose that because, well, everything is asynchronous with message passing. If you use a gen server call, you can kind of replicate it, but it's much easier and much cleaner to have a solution of asking for permission to do something. And asking for permission requires you to isolate your central bottleneck. Irina this morning mentioned it with finding out that they were how much CPU you can use for all your tasks. That was a central bottleneck. And you put something in there that lets you ask, can I do more, please? She or people at Ubiquiti use jobs for that. There's other options. Job is a cool one, but that's how you do it. I'm going to talk a bit more about load shedding because that was briefly glossed over. Random drop is one of the options. It's especially cool if you can drop your data on the source producing it. That's very frequent for metrics. If you're looking at Folsom code or stuff like that, they usually will just send something like, well, I'm going to send 5% of the requests, And each of the value I'm going to send, I'm going to multiply it by 20, so it's worth more than usual. So you get, over time, with many, many numbers, an accurate picture, statistically speaking, with only a fraction of the bandwidth. And this is something that I'm sure Brian could tell you about. If you're generating 500 metrics for every request, so you get 1 million requests a second, you're generating 500 million metrics every time, and it gets to be harder to scale up your metric system than scaling your actual system. Random drop is good for that. Queue buffers. A queue buffer will work exactly the way a queue back pressure mechanism will work, in that you just put jobs in there, accumulate them, and at some point, the difference is that in the back pressure system, you say, I can no longer accept a job. In load shedding, you just take an element at either end and you drop them on the floor. You do it silently, and you just decide that that's not going to be processed. If you take it at the oldest end of the queue, it means that you think that the old messages are less valuable than new ones, and you can do the other side and pick it that way. It's especially cool if you need messages in order. So first come, first served, that kind of deal. The problem with that one is that if I'm at, let's say that's orange message in there. If the one before me is slow to process, I accumulate the time that the other task took. So if every task takes like 5 milliseconds longer than you need, at the 100th task, you're now at like 500 milliseconds longer, and you haven't even used that to process, but the user had to wait for that. So when you're dealing with low latency system, what you want is a stack. And you've all experienced a stack if you call customer support and waited more than like 5 minutes. I'm sure it happened to everybody in there. So what you do with a phone system is that if you want 99% of the customers to be happy, you have to pick one jerk somewhere that's going to wait at the end and be really, really unhappy about waiting. So if you're ready to wait and you started waiting, you're just going to say, well, that person is already unhappy about it. It doesn't matter if we make that person even matter. As long as the other people are happy, that one can wait for 5 days already unhappy, might leave us soon. So you just keep serving the other ones fast, and you get 99 or 99.9% of your customers happy with fast response times, and a few that might leave you anyway, they were already pissed off to begin with. So a stack is cool for that. The problem is that you lose the requirement for ordering. It comes in any kind of order you can have depending on what rate you are consuming stuff. And that's usually the best for latency. If you can get it, you need low latency. Consider using stack buffers instead of queues. Overload handling. So options, roll your own. That's usually not a great idea. It works well though. You've got the OS monitor application. That's where MEM SOP, CPU SOP, and disk SOP are that Irina mentioned earlier today. SASL has something called the overload module that has a fancy equation in there that lets you decide at which rate you're going to drop elements and stuff. You've got jobs that is mentioned right there that Irina mentioned earlier today. Safety valve is Jesper Lewis Anderson's version of jobs with less flexibility but more systematic testing in what it does. So the idea is that Jesper looked at jobs, found a few bugs, fixed them, and figured out that it was very, very hard to extract good, predictable models out of that application to test them with quick check. Decided to rewrite it with safety valve with a lot less flexibility, but a usually more predictable behavior in that. I want to talk about Klarna and circuit breaker. Circuit breaker is different than the others in that you will specify how many times you want, let's say, a call to a database to fail or take too long. And after that, well, you just turn it off for a given period of time so that it can cool down and stuff like that. You blow a fuse and you just stop it. And it's a form of back pressure that's especially nice if you want to have certain quality of services, but don't necessarily know how to figure out the properties of it. There's PO Box. PO Box is an application that we rolled around at Heroku, and that one is to handle load shedding. So we've got the queue buffer, we've got the stack buffers that can be emptied from either side, and it's pretty nice if you want to get predictable interface to load shedding. The things that it does is that it tells you about losses. I'm going to come back to that very, very soon. So I asked this question to Irina. I'm sorry I'm using you all the time as an example. Earlier today, what do you tell customers when something goes wrong? And usually, if you haven't thought about it in advance, you're going to be having a really hard time telling them what to do. So two things that you need to necessarily keep in mind when you design your system, and you want to keep it in mind because the network is terrible, and if you assume the network is not terrible, you're going to have a never crappier time. You need to respect the end-to-end principle. End-to-end principle states that you don't do something such as fire and forget somewhere in the middle of your chain. It should be possible to verify from the sender and the final receiver that everything in the communication went fine. That means being able to either poll the remote end or the remote hand as a way to validate that the task went fine. If you don't have that, you never have a good way to know if the message at the end made it properly. And this is a principle that you should really, really care about and look into, because it was talked about in the first times around in the 70s and were used to design TCP. And if you ignore that, you're ignoring 40 years of computer science. So please don't. You want to make idempotent APIs. And idempotency in that case means that if you repeat an operation many times, it ends up giving you a stable state. So if you're looking at HTTP, you have the put operation where you just change the file and put a new one. That one is idempotent if you just upload the new file, because whatever you do, it's going to crush it with the version you want in there. If you're using a patch mechanism, for example, you're not going to get that because the same patch could be applied many times and yield a different file as it gets operated on multiple times. And idempotence is hard to design for if you think of it like the put operation and just crushing the file. So a cool tip for that one is that you give something a transaction ID or an order ID or something like that. That's a unique value that you can poll for. You put that into your request and then you send it, and you can just send that request with the same ID many times, and the system at the other end should be able to look at that ID and say, I already processed that stable, here's the result you wanted, and just do no work. But if you design your application to have that end-to-end principle, when you can know from the client side that everything worked at the other side and everything like that, and you don't trust anything in the middle, and that the API is idempotent in that you can retry it many times, it won't matter if you block a request because you're being overloaded, it can be retried, and it won't matter if you drop it on the floor because it can be retried again. So you want to tell people about losses. Tell them about losses. In practice, what we found out, Heroku, we have this logging router that just takes the log messages from applications, and we don't have a way to deny them, so we have to shed the load all the time. That when we're overloaded, we just count how many messages we drop on the floor. And then when we're done, we send a message in the log lines of people like we dropped 500 messages because it was overloaded. And in practice, you'll find out that this is entirely satisfactory for most of your customers. They're going to look at that and say, yeah, I'm just producing too much data, and they're not going to think that there's some hidden magical bug in that the output they thought would be there is no longer there. If you tell them what you did and why you did it, people are usually understanding about that. It's also about communication. You want to put usage limits, however high. So one of the questions that was asked earlier today was about fairness and how do you ensure fairness between people. So you can have a usage limit that's entirely global to your system, which is what we see if we have a single queue of tasks and then it gets chopped off. You can put usage limits per account so that you make sure that if you have somebody is being a bit of a jerk and sending you 1 billion requests while everybody else is doing 100, and you have a 10,000 limit at any given time, that person is not starving out every other customers. So what you do is that you put a usage limit per account. Salespeople love that because they can look at the important customer and give them like 1.5 the regular amount for a bit like 10 times the price. They're super happy about that. And usually it ensures some level of fairness. The risk of doing that is that every application has this thing called the margin of error. So you have this laid back area above the red line when everything is fine, you don't have to worry about it. And then you have the danger zone. And the danger zone is the point where you get something like, I don't know, 75 to 95% of your load. And you see that the system, and you look at your chart, it's starting to get choppy. The behavior becomes unpredictable. You don't know what's happening. It's the equivalent of blowing up a balloon and feeling it's going to explode in your face. And what happens is that as we spend more and more time in the danger zone, we get used to that choppy behavior, and the margin of error that we have mentally gets shifted closer and closer to that margin there where everything explodes. So when you have per account limits or something like that, the more users you have, the more slowly you get into the danger zone and stay there. So you have to be very careful and train the people who are going to handle your system and operate it to recognize when they're in the danger zone. I just like seeing danger zone a lot. And to start reacting about it. And the thing is that when you start first shifting in there, you might want to start thinking about scaling up your stuff. Because if you start thinking about scaling up right there, instead of having, I don't know, 3 months to do everything, you might only have 5 days. And if you have 5 days, you don't have the time to do something well tested, you might just be in trouble with your system, and then everybody hates you. Except your mom. Your mom always loves you. So yeah, to get to know the danger zones, that stuff you have to get your hands dirty. And this is a bit of a taboo in multiple communities, but I love working directly in production. Fortunately, we're short on time, and Brian mentioned a lot of that stuff about monitoring and what you can use. But I want to say here, this is from Programming 4th, 2011 by Stephen Pelk. Debugging is not an art. Debugging is a science. So we find a problem, and then we have to gather data and look at it, and then form a hypothesis about why this should be crashing right now. And once you have that, you try to replicate the crash. And if you cannot reproduce it, the entire process ends there. And then you can test it and do that kind of circle. And if you have very, very poor data, then you get this very, very repeated cycle that might never end. So gathering data and having an easy way to form an experiment, super important. Fortunately, Erlang is made for that, and this is what Brian talked about the most. You can introspect everything. You have traces, you have processes accessible. You can look into the garbage collection, how much memory you're doing for. You can look into the network. You have port info that lets you know which connection is actually using that many packets or how much bandwidth it's consuming. You can look at other nodes, connect to them, and do a lot of stuff in there. So I have written the Recon application to deal with that. Also lets you do safe tracing in production. Use it, love it, give me feedback. And all the stuff I didn't have the time to cover because we're in a hurry is in Stuff Goes Bad, Erlang, and Anger that... Oh? We're on time! More time. Okay, cool. So I already raced through everything, so that's... so that's worth nothing. But yeah, most of the stuff is in that free book that's at that website that you can download as a PDF. I tried to keep it short. Learning from Erlang with 600 monstrous pages. That one is under 100. And yeah, Heroku is hiring. So we can take the time for questions, I guess, because we got plenty of time.
Go back to the previous slide, please.
That one?
No. There you go.
That one? Okay. All right. Yeah.
You mentioned a tool that you built, and I didn't really catch the name of it.
Recon, R-E-C-O-N. I usually plan the demo for that, but now, given how short I was, I didn't prepare it, and now we have the time and no demo. But I have exercises in that book that use it to show you how to use it and try to debug production nodes and stuff like that, introspect stuff. More questions? All right, then. I guess we're over and within the time limits. Thank you.